Good morning, everybody, and welcome to today's Tech Talk. I'm Janki Gattu, a certified GIS professional, and I'm working as a GIS specialist with Geosys Enterprise Solutions Private Limited, which is an ISO 9001 and 2015 certified organization, which is an ISRI partner company. Today, we are going to have a Tech Talk on creating digital twins using GIS. So let's understand what is this digital twin and what is that we are going to learn in today's Tech Talk. In simple terms, if you want to say a digital twin is nothing but a virtual representation of the real world entity. So that can be your objects, that can be the processes with relation to the objects, that can be the behaviors, that can be patterns, anything that is present on the physical world. If you are representing it virtually, then that is nothing but a digital twin. So, and this is a buzzword in the very recent days where cities around the world are in different stages of creating digital twins for planning better urban activities and planning ahead of the disasters for flood prediction and seeing the line of sight, understanding the viewshed, and creating show impact analysis and much more. Okay. And in this Tech Talk, we are going to achieve all this by using a Lidar point cloud data, and from which we are going to extract our buildings, which is going to be a 3D representation of our neighborhood. So, and the agenda for today is we are going to learn the concept of digital twin, and we are going to see what is a Lidar data and how we create a LiDAR data set and how we can process the LiDAR data, classify the LiDAR data, create building footprints, and then create the realistic 3D buildings using our LiDAR point cloud data. So as I just told you, a digital twin is nothing but a visual representation of the real world entity, which includes your physical objects, processes, relationships, and their behaviors. And GIS plays a very vital role in creating of these digital twins. The reason being all the physical processes, objects, everything you're trying to get into a digital twin, but when you add GIS, the location information to it, it is much more valuable and you can derive a lot of insights out of that location intelligence. And that is possible when you are integrating your digital twin with GIS. So GIS creates digital twins of the natural and built-in environments, and it uniquely integrates many types of digital models. So geospatial technology connects different types of data and systems to create a single view that can be accessed throughout the complete project, which means like if you are taking a project and all the physical objects of that particular object, the behavior, the pattern, the relationship, the processes involved in that particular project can be achieved using our GIS with digital twin, which enhances the process in capturing of the data, in integrating GIS with other softwares, other data, other models, and which will further help us for real-time visualization of the data to do better advanced analysis and to work on automations for doing the predictions using your AML and deep learning models. And we can also further collaborate and share the data with other users, other departments, depending on the project that we are working on. So what is this life cycle of digital twin? So it is pretty similar to our GIS cycle on how we do the process, how we create the data, which means your capturing of the features, the data capture, and then how we integrate the data with other softwares or systems. Let us suppose I will take an example of some sensors, which is your IoT devices, which we put it, let us suppose you want to get real-time weather information and you want to identify like where rainfall is more, where rainfall is less. So you can put sensors at different locations in your city, and you can do an IoT model, a sensor fixed at different locations where the sensor triggers when there is a rain, and then it gives you real-time information. It can be like the amount of rainfall, the flow in which the water is flowing. So whatever parameters you want, you can capture it within that sensor and it triggers, and that data is collected and it is transferred to your devices, which is nothing but your data capture. And you are integrating this data with different other systems. Like I am using the data that is captured by the sensor with my GIS location intelligence, which I'm capturing the data in real time and processing my GIS data. So where I can have real time information and I can visualize the data, like how much of rainfall is there at that particular location and what is the kind of impact that it is having on the traffic at this particular point of time. I can have the real time visualization where I can use the dashboards or reporting tools for the visualization of the data. And once you have the data available with you, you can always do further analysis and then predict like, okay, if at all, if the next rainfall is going to come on so and so date, what would be the impact? So you can always analyze the existing data and predict the models using your automation tools like artificial intelligence, machine learning, and deep learning tools. And then you can simulate the actual information, and then you can find out how your next scenario would be like and what kind of precautions has to be taken in order to avoid this. Okay, and further, if you want to enhance the data and if you want to use the data, you can share this data with different groups, different departments, different people. Based on your project, based on upon the confidentiality of your data, you can select and share the data and collaborate with different groups to engage the data, to enhance the data, and to create various kinds of applications from the data and change the system of record to system of engagement. Because we don't want the data to be stored as a record in our systems, in our local systems. We want it captured into an application. So this entire life cycle, we are calling it as digital twin life cycle, which is integrated with or enhanced or become powerful with our RGS solution. So interconnecting GIS and digital twins. So we have to understand like where it is used, how it is being used. If you see like in order to map your landscapes, in order to find the highs and lows on the surface of the earth, in order to find the impacts on the environment, in order to understand your landscape, in order to see your structures, building information modeling, how it was created, and inside of the building, if you want to understand, you map the indoors and you see like how it is actually planned, and do you have proper storage spaces, is it planned properly. And not only that, you can also work with your utilities, gas pipelines, and your telecommunication networks, so whatnot. You can work with n number of things when you're integrating your GIS with your digital twin. So GIS allows you to extract the data, as we have seen in the previous slide. So GIS helps you to capture the data, to integrate the data, to analyze the data, and to visualize, predict, and then to share the data and collaborate with other teams. So is it really simple or is it more complicated, is the question. GIS has been evolving like for few decades now, and in the past 6 to 7 years, GIS, the way people started using GIS has changed very drastically, and it has got n number of applications in its usage, where we are using GIS as one of the prominent tools in refined decision making by the stakeholders. So as such, like the business requirements has been evolved, and there were lots of integrations with different technologies, tools, softwares, and everything. As such, there was a lot of complexities that has been involved. So GIS is helping you to find a solution for all your problems. So let's understand a case study. So now we are going to take a case study which is located in Denmark, and I'm going to take a place, Tuborghaven, and then I'm going to use this Tuborg place and then do my analysis and show you how you can capture your 3D realistic buildings. And why I am taking this particular place is, this place is earlier was a land with limited number of features, but now this particular area has been redeveloped with mixed use neighborhood. So it has different kinds of buildings, and it has redeveloped a lot than it was there earlier. So we wanted to capture the 3D buildings of that particular place, which will help me for planning the urban activities, what kind of activities can be taken place for flood prediction analysis and all. So as a GIS analyst or remote sensing specialist in your area, what you have to do is you have to give a solution and represent your data in 3D realistic buildings so that they can do their further analysis when they plan the urban activities or flood prediction. So here we are going to take the input as Lidar data, which is Lidar point cloud data, and we are going to use a software called as an ArcGIS Pro software, and using this Lidar data and using our ArcGIS Pro product, we are going to extract the 3D buildings, and then we are going to create and classify our Lidar dataset, which we call it as LAS dataset, and extract our digital elevation model and get the 2D buildings and extract our 3D multi-patch buildings. So let's understand what is this digital elevation model. So digital elevation model will have your X, Y, and Z coordinates, which is your location and the elevation values. So, and it is a raster GIS data. And what is this digital elevation model? What does it represent? It just represents your bare earth, the just topographic surface of your earth. It will not show any physical objects that are present, like either buildings, either mountains, trees. It is not going to show you anything. It is just going to show you the highs and lows on the surface of the earth using a digital elevation model. And we are, as this is a raster data, obviously you know that each and every cell in the raster will have X and Y coordinates, but this digital elevation model will also have its Z coordinates, which is like an elevation of each and every raster cell. And where are we going to use this digital elevation model? So if you want to do viewshed analysis, if you want to do line of sight analysis, surface analysis, subsurface analysis, for all of this, you need your digital elevation model in order to understand your Earth's surface. And if your digital elevation model, if the cell sizes are very, if you have small grid spacing, excuse me, can you please mute your microphones? All right, thank you. And if we have if the space between two different cells is very small, obviously you're looking for more details in your area of interest, and that's where we are going to use our digital elevation model, and we are going to generate that using our Lidar data. And what is this Lidar data we have been talking about since the beginning of this tech talk? Is what is this Lidar? So the Lidar is nothing but light detection and ranging. And this is one of the remote sensing techniques which we use when we have like samples of densely samples, we will be using this lidar techniques to capture our information. So where is this lidar used is basically it is used in airborne laser mapping applications because it is cost effective, and you will just pass the rays to the surface and under the surface of the earth, and then you're going to capture the information with the light. So as such, this generates point cloud data sets which can be managed, visualized, analyzed, and shared across your ArcGIS platform. And the data which you generate, the point cloud data, would be in the form of .las files, which is your las format. And the point cloud data is nothing but the data points that we generate from our topographical area. So we'll see like how to process the LiDAR data and extract our 3D buildings in today's Tech Talk. So for which we are going to take the last data sets, a last point cloud information, and then create a last data set, then classify the point cloud information. And we are going to classify the buildings, and we are going to generate a digital elevation model, and we are going to extract 2D buildings and 3D building features. So here is the workflow for generating the realistic 3D building. So we are going to classify our last data set. So we are going to get this kind of image when we generate the last data set, and we classify that last data ground control points, and then we create a digital elevation model and we classify this. We remove the noise from the last data sets, and then we create buildings, 2D buildings, and we generate the realistic 3D buildings like as you are seeing here. So let's go ahead with our demonstration. So if you have any queries, you can make a note of it, and we can see all the queries at the end of this TikTok. So as I told you, this is a place in Denmark, and this area is Tuborg area, and if you see, there are like a lot of high-rise buildings which you are seeing in this area, and this area is having a lot of buildings because it is a redeveloped mixed-use neighborhood in the Denmark area. So we are going to proceed with this data, and before I go ahead, I will show you. So if you see here, this is my Tuborg data, and I have taken the point cloud information, which is the last data set. As I told you, .las is nothing but your point cloud information. So I have one file, and this is the other file which I have. And this is my ortho photo, the realistic view of the image which you are seeing here. I will turn off it and I will show you. So I have to, this is the area of our area of interest. This is the Tuborg area which you're seeing here. And then I have just taken the base map, which is World Topographic Base Map, and I am having this ortho photo to see like how my buildings are in real time. Okay, so we don't have any information here except your last files, which are your point cloud information. So from here, we are going to generate all the respected outputs. Okay, so let's get started. Okay, so I have taken this data and have created a project which is our building extraction project, and you have seen the data inputs which we have, and now we will start working on how we can create our last data set. So you can have n number of point cloud information, and all this point cloud information can be captured into a data set. So how do we create that last data set is by right clicking on this folder and going to new, And can you see here it is a last data set. So, and we can give the name Bog 7. So this is LAST, which is the last data set, and this is basically an empty data set, last data set, which we have created just now. It doesn't have any point cloud information in it. So we are going to add this two point cloud data into our data set. So how do we add that information? Okay, so before we go ahead and before we add the data of this last files, so we'll first see like what properties does this last data set have. Okay, so as of now, we'll go to the last files. Did we add last files? As of now, we did not, because the two last files are here. It was just created. So you can click on add files here, and you can browse to your path, last data, and these are the two last files which I have, and I'm adding those two files here. And if you see here, how many point clouds are there in one file? About 5 million, and in the second file I have about 3 million. And the point spacing means the distance between 2 points in your LiDAR data is nothing but your point spacing. So this is about like a 0.3, and this is also near about 0.3, which we have here. Okay, and then now we will see the properties of this last data set. Let's go to the general, and how many last files we have added. As of now, we have added two last files. If you have more last files, you can add more last files as well. And you can see, as I told you, like we'll be able to generate the elevation model also here, the digital elevation model. So you should always see like what are the units of it. It is in XY, your coordinate system is in meters, and your elevation is also in your meters. And you can see the minimum and maximum values of X, Y, and Z coordinates. And the second one in your properties is your statistics. And if you see the statistics here, you have something called classification code. So whenever you have added this data sets, as of now you haven't done any kind of classification, so obviously it is categorized as unassigned classified data. And your point count is your 5 million and 3 million, which is about 8 million of point cloud information together, or unassigned point cloud information which we have. Okay, and obviously when we are working in GIS or location intelligence environment, you have to always keep in mind your coordinate system. What coordinate system does your file have? So I have this ETRS 1989 UTM zone 32 north. So this is just for information, like what properties does it have. I'm just showing you. So click on OK. Okay, and as of now I have added this point cloud information into the data set, but this data set has not been added to my table of contents for it to be shown here. So what I will do is I will turn this off, and I will add the last data set which we have created just now with two last files. Okay, so how do I add this? Right click and click to add to current map. So it is getting loaded. We have to wait for the system to process. Generally in 3D LiDAR data and all, no, the system takes a bit of time for getting processed. So this is our LiDAR data set, the point cloud data which we added into our data set. So this is how it appears. And if you go to your table of contents, and if you expand this, you have only these colors as symbology here, and all the lowest points are shown in this blue color, and wherever like you have higher points like the buildings and all, which has like elevations and all, that are shown in your red color. Okay. And now if you want to see individual point files, okay, so all we have to do is I'll just turn this off so that we can zoom little fast and come back. Let's wait for the system to get processed. Can you see? So these are all the point cloud information which we have. So I'm zooming out back. Okay, so I'll just zoom it back to its area. So give me a minute. Okay, so we will use, I'll use the base map. Let me turn it on. It will take a bit of time to load the data. So in between I can save this project. So we have the last data set on our base map. And now we have taken the point files, the first thing, and then we have created a last data set. That's the second point. And the third point is we have added the last data set to our table of contents, and we have seen the point cloud information. Okay, now the first step that we are going to do is to classify the last data set. So classifying the last ground points, I'm sorry. Okay, so how we do that? So this is my last data set, and if you go to this last data set layer, so we'll have this last points. So filter last points by classification and return values. So let me click on this last points, and it will show me the last filter and what all it is having. So what I will do is, so I will go to symbology first. So I have this information. One second. So I'm going to symbolize my last data set using the symbolize layer using points. So I'm going to select this class. I'm just expanding this. So if you have seen earlier, like all this data was unclassified. Now when I have clicked on that class, it is dividing this into different values here. By default, it is turning into different classification values. So on the last data set, now we can use our, now it is classified. So let's go back, and we will take our geo processing tools, and what we want to classify here, we want to classify our the data which you are seeing here. So we have something called as a classify last information. So you can say like a classify last ground data, classifies ground points from last data. So as of now we have only point cloud information, so you can take that. and we can process the information. So let me give the input as last data set, and ground detection method is standard classification, and then we are just leaving the defaults as it is, and then we are going to click on run. Now when this gets processed, you will get all the ground points here on the image. It will take a bit of time for processing, so we have to wait. So as of now, you can see whatever is on the ground, which doesn't have any kind of elevation, only those points have been generated, which you can see it in the brown color. Okay. So let me go to the contents, and you can see here, this is how it has been classified. Only the ground points have been generated here. Okay. Now what we will do is we will create a digital elevation model here. So for creating this, what we need to take is, we used to take the last points and then set some properties. So what we will do is, I'm selecting this last data set, and here under last data set layer, we have this last points, and we have something called last filter. So select the last point properties to filter the last data set. So you can filter it using the classification codes here. So what I will do is, I don't want any values which are unassigned. All the unassigned values are the gray ones. So and all the ground values are this brown one. So I will just select the checkbox and I will click on OK. So if you have seen, all the unassigned points, which means like the other points, have disappeared from your map here. Now we can use the tool called as last dataset to raster, because now I have this raster dataset, and I have just taken the ground control points. From here, I'm going to generate my digital elevation model, for which I have to go back, and then I have to take this tool, last dataset to raster. So if you see, it creates a raster using elevation, intensity, or RGB value stored in the LiDAR points referenced by LiDAR dataset. So we can open this. Okay. And input last dataset. So my last data is the dataset which I have created. And now what I'm going to do, I'm going to generate a digital elevation model. So I've given the digital elevation model name. And then there are like different types of interpolation methods which we can use. So I'm going to take triangulation method, which is most popular method when we are doing interpolation. And then here I'm going to use the natural neighborhood method. And then the sampling value, whatever we are going to here, we are going to give it as 0.5. So I just want to take 0.5 as a sampling value here, and then I'm going to click on run. So any idea like why we are taking 0.3? Because when we have seen the last data points, the point spacing between 2 points is nearly 2.3. So I'm just rounding it off to a value of 0.5, and then I'm taking this. As there are like 8 million points, so the system will take time for generating the output. I'm turning this layer off so that we can see our distal elevation model. So this is the distal elevation model of this particular landscape that has been generated from our last data set. Now we have to classify the last noise points. So whenever we create the data, there will be some values which may be very high, which may be very less, and that creates like a lot of noise in the data. So unless and until you remove those kind of outliers and the noise from your data, you cannot say that data is a perfect data for doing your analysis. Okay. So let me go to geoprocessing. So let me take the tool, classify. So you have a classify last noise. So we are going to classify our LiDAR point information, and we are going to classify that noise data. So when we come here, let me go back once. So first we have to see that this layer is selected, and we have to see the last points, whether this was properly taken or not, and then we have to proceed here. So we are going to uncheck the ground, and then we are going to take the unassigned values again, and then we are going to run this tool from the geoprocessing tool, and we are going to remove the noise. So what is this data set which we have is our last data set. So the elevation is taken from the ground, so it is a relative height from the ground, and we are going to take the minimum height and the maximum height values. So I'm taking minimum height, and I'm going to, as you know, the like the information is in meters here, so I'm going to take that, and then I'm going to click on run. This is only removing the minimum height noise values. Okay. So height detection. So yeah, the reason is like I have not given the elevation. That is the reason it is throwing me an error. That should be the reason. Okay, let me run this tool again. So we are going to classify our last noise information with the minimum height value. Okay. And now we also need to identify the values with high noise. So here we are going to take the same thing. Here we are going to take absolute height, because earlier the lowest elevation we have to take. So that is the reason we have taken relative from ground. Now we are going to take the height. So that is the reason we are taking absolute height. And then we are going to give the maximum height type and remove this minimum value. And then click on run so that we will get the high noise values. And this low noise and high noise values would be generated, where we can see that information in our last point data. I'll show you. Here you cannot see it. Here you will be able to see it. So earlier we have only unassigned when we have taken the data. Later on we have differentiated between ground and unassigned. Now we have generated noise and the low noise and the high noise values. So what we can do is we can remove this unassigned ground, and we can just take these two values and see like what is our noise. So let us run and see like what input does it generate. Can you see here? These are the noise values in our data, and noise has to be removed before we go ahead. Okay. So let's go back and click on this unassigned, because we want to further classify this. So take that and remove all others and click on OK. Okay. Now we have to classify our buildings here, whatever elevations you have. No? So that we have to classify the information. So what I will do is I will run a tool, classify last building. So if you see here, it basically classifies the rooftops and the buildings here. Again, you have to take the same data set. And the minimum rooftop height generally it would be like 2 meters, and minimum area like 10 square meters we can take. And we can use a classification method. Different types are there, so we can select any method depending on our requirement. So I'm choosing like a aggressive method, and then I'm clicking on run. So earlier we have unassigned, then we have generated ground, then we have generated the noise, low noise and high noise values. So when now we are generating the building information. So we also need to get the building information in our last points here. I'm saving the project in between. So if you open this last points, and if you see earlier we have unassigned data, then we have ground data, then we have noise, high, low noise, high noise values. Now we have building last values which were classified. Now, which is this one only, it is just the classification that we are doing internally on the last data. Now we need to generate the building rasters. Okay, now this is all the last data set. Now we have to generate the building raster data. So how do we generate it? So let me go here to catalog, and when I open maps, I have a scene layer. That is the reason it is showing me in 3D, but I want it in 2D. So right click and click on convert and then click on map. So now it generates a 2D map of the same data where I can see in 2D. So I can rename it as 2D map. It is loading, so I'm just waiting for the data to get loaded. In 2D map, we are getting the 3D map, 2D map from our 3D scene. We'll go back to our geoprocessing and we will use the last point statistics as raster layer. So it basically what it does, it is creates a raster whose cell values reflect statistical information about measurements from last files referenced by last dataset. So let me take this and I'm going to take the dataset. So what I'm doing is whatever the point information I have as buildings, I'm going to convert that data into raster data. So which I'm calling it as building raster. So there are different class codes. So I'm going to use most frequent class code and give the sampling size. Earlier, if you remember, we are going to take 0.5 and then we are going to click on run so that we will get our building raster information here. Go to contents and see. Earlier we have this digital elevation model, so I'm just turning it off. And this was my point cloud information. Okay, so I have this building raster information that has been generated. So I'm going to change the symbology here. So let this get generated. This is how the data is for now, which is our building raster information. Okay. So now we can generate a building feature class. So normally when we have a raster, what we will do is we will convert that raster to a polygon feature uh, using the polygon tool. So I will also on the same tool. raster to polygon. So I'm going to convert the raster dataset to polygon features here. So I have the building rasters and I'm going to convert that raster to polygons. So I'm going to click on save. So our raw buildings information has been generated. So we can change the value. Change the symbology. I'm just turning off unnecessary layers. So I'm just waiting for the system to load the data. So now we can clean up the buildings. And what we can do is we can use the layer by attribute table and we can select like based on the some parameters we can select the features and then we can correct it. So what I'll do is I'll select this and then go to map and then click on select by attributes. So I'm going to take a new selection and then I'm going to give the area so it is showing me all the areas here which has been selected. Now what I will do is I will eliminate all this point internally, like if you see these are like point gaps which a polygon is having. So it will eliminate all those using our eliminate polygon part 2 and it will do it only on our selection of the buildings which we have selected. So let me go back and let me search for the tool. Eliminate polygon part. So it basically creates an output feature class and it removes all the holes that are there within this building. Let us suppose if you see here. So for this I have the raw one and then I'm going to clean up the buildings. I'm going to give the name as uh, clean up the buildings. Okay. And then I'm going to take the condition as area and then I'm going to create this. Now clear the selection. And if you see like wherever the buildings are, like it is properly capturing the building information. But normally the buildings, if you see, I'm removing all this data and I will recreate it again. Just give me a minute. So let me go to geoprocessing and I will run the tools again. So I'm going to take this input data and I'm going to give this output, and I'm going with the aggressive classification method, and I'm going to click on run. Let's wait for the system to generate the output. Let me go back once here and check. Hmm. clean building raster raw. I'm removing all this which I have generated it, so I'm deleting it. So let me go back here and let me run this classify building tool. And then I'm going to take my last data set and I'm going to set the height to 2 meters and then 10 square meters. Go for aggressive classification method and click on run. I'm saving this project. So let me go here and let me see the buildings if it has classified properly or not. So let me take the swipe tool. If you see here, the buildings were generated properly. If I swipe and if I show you here, you can see it is properly generated. Now I have saved this. Now I will extract the building footprints. So let me go back to the geoprocessing tool and before I go ahead, I want to convert this scene to 2D layer for doing the for creating the 2D information. So what I will do is I'll click on scene and I'll click on convert and I'll click on 2D map. So all this data would be generated into 2D. So in 2D, you can see the buildings in 2D that has been generated here. Let me rename this. 2D map. For our reference purpose, if you want, like we can turn on this orthophoto. So now it is clear, right? So if you see here, it is classified properly. Okay. Go to geoprocessing and let's run this last point statistics as raster. And then create the buildings raster information. So from the last data set, I'm going to create the building raster information. And the method is most frequent class code. And then I'm going to give the sampling size. And I'm going to click on run. Let's wait for a minute for the system to generate the output. So now what we are doing is created a building raster file from our last dataset. If we see in our table of contents, we can see the building raster. Now I want to give this symbology. Which you are seeing here are all our raster buildings which have been generated from the point information. So these are all the buildings that has been generated as a raster. But like for us to create features, 2D features, like you have to convert this raster to a polygon feature. So I will go to my geoprocessing toolbox and then I will click on raster to polygon tool. And I have my input building raster. And whatever the building that I am going to generate from my raster information is a raw building. So which means like it is not clean. So it just converts the raster data to the vector data. Buildings. I'm going to give this information as raw information because it is just converting the features. Okay. And click on run. Let's wait for the system to generate the polygon features for the buildings. Yeah, so earlier we have whatever we have seen. The first one is a last data set, then the last data set point cloud information. The second, which we have seen, is a raster data, and now what we have seen is a polygon data. So go back to the contents and see, this is basically, earlier it was a continuous data, raster data. Now this is like our vector information. So we have this attribute data also, we can open and see. So it has given ID for each and everything, and it has generated code, shape ID, and everything. So what I will do is I will change the symbology here. I'm turning off the raster layer here. So these are my raw buildings. Now, if you see here, let me zoom and show you. Though the building footprints have been generated, if you can see there are like lot of holes that has been generated within the building. So which is not correct. This has to be a complete polygon where it has to remove all those gaps. So for which like we need to clean up the buildings. Okay, for which we are going to run a tool now. Select by attributes. So what I have to select the raw buildings, and I'm going for a new selection, and I'm going to select like where area is more than 70, which means like all this because if you take like less than 70, all the smaller features would be selected, but we just want only the features within the building. So I'm just selecting this and I'm clicking on apply and OK. So it has selected only the gaps that are there with the building. And now my intention is to remove the gaps within the building, for which like I have a tool called as eliminate polygon part. I run this tool. So when I give input as a building raw, it will take only the selected features. So it is taking 171 records which are selected, and then I'm going to give the name as buildings clean, as I'm cleaning all the information on the buildings, and I'm giving the area, and I'm clicking on run. So when I run this, all this gap should be eliminated. So that is what we're writing. We're running the tool eliminate the part. We should be able to see like building features. So let me click selection. And earlier, whenever you have seen like there are like lot of gaps in each and every polygon, but you can see here now we don't have any gaps within this polygon features. But if you zoom properly and if you see like this is not the regular polygon which we will be having. We'll have the lines as straight lines, right, when we draw a building. But here if you see the edges are not smooth, so it is like a random image. So what we can do is we can regularize that building footprints. regularized building footprints, which means like it whatever the different shapes we have on the outline of the building, that would be smoothened here. A smooth a smoother polygon would be generated. So the input is our building clean, and then I'm going to generate footprints. Right angle method, which means like every coordinate it will make sure that it is a right angle properly. Tolerance, densification, and precision, which means the maximum tolerance, like how far it should take and how it should give the values and all. So we are clicking on run so that the different shapes where we have irregular shapes on the edge of the building would be turned into. Okay, I'm running the tool once again. That is, as it has generated some error. Okay, and if you see now, earlier like these were in different shapes on the edges, but if you see, it is in a proper shape. I'll go to the contents. I'll turn this earlier layers. I'll turn off this earlier layers, and this is the building footprint that is generated. So if you see here, the edges are more refined than what it was earlier. This is how we can generate our buildings, and we can clean up the data. So I'm zooming into a location. So you can actually do a verification, and you can remove unwanted things if they have been generated. Now I can see like this is one polygon which has been generated, and this is one polygon which has been generated. So what I will do is I'll go to edit, and I'm clicking on select, and I'm deleting it. So I don't have unnecessary polygons that has been generated here, and I'm doing the save edits. Okay. Now if you zoom and see, this building is okay, but if you see, this building has not been generated properly, and there are like few things which we have to do, though automatically everything is generated, but these are like few quality checks that we have to do before we give the output. So again, go to edit, and then we have to reshape that particular building here. So before that, I'm selecting it. Okay, and then I'm going to reshape it. What happened? So let me redo it once again. 1 second. I don't know why this tool is not working.
Maybe you select only other elements.
So I'm going to my contents and I'm zooming out the location here. So you can see here, most of the inputs have been generated, and we can create this multi-patch layer on the building footprint and take a copy of it, and then go to your catalog, click on scene and right click and click on paste. So I'm going to my 2D map and then I'm copying it. And then come to the scene tab and then click on paste. Now we have to create the multi-patch 3D buildings here in the scene layer. So what I will do is I will go to this geoprocessing tool and then I'll click on this last building multi-patch. Give the last data set which you have and the input features. Now you have this building footprints and let it be there as building classified points, and then you can select the ground height as a raster layer, and you have to take the digital elevation model and here you write it as multi-patch 3D buildings. And give the same tolerance and click on run. Now we'll be able to see those buildings in 3D once the output is generated. I've turned on the 2D buildings layer. I have turned off the 2D buildings layer and the other information because I want to see the 3D multi-patch buildings. So whenever we work with the 3D data, Lidar data and all, it takes time for the system to process information. Let's wait for the system to load the features. So these are the buildings that has been generated, but it seems to be in white color. So let me change the color. So these are the buildings that has been generated. Okay, now we'll go to our elevation surface and here we will add our elevation layer. And our elevation layer is our digital elevation model which we have generated. Click on OK. Now once we added all the elevation and all which we are seeing will be adjusted now. And now I'm saving the project. Okay, so in this TechTalk, what we have did is we have taken two last files, point out files, and we create a last datasets, and then we have classified as unassigned, and then we have classified the last round we have converted the last data set to raster, and then we created the removed the noise values, and then we created last buildings, and then we generated the last point statistics, and then we turned the raster to a polygon where we got the building features, and then we have selected the gaps within the features using select by layer attribute. Then we removed all those gaps within a polygon using eliminate polygon part, and then when we have got the output, all our building edges were not smooth and it was in a zigzag manner which we have uh, characterized the building footprint, and then we finally generate our building multi-patch. We can close the curtain. So if you have any questions, you can ask me now. Any other questions?
Yes, ma'am.
Yes, please.
Ma'am, I am here. Hello.
Yes, Anil.
Ma'am,
Yes,
like,
Anil, please tell me.
yeah. Assuming that the distant technology is widely used already, which is the sector which is benefiting most among all these sectors? Like, which is the sector which uses digital twin technology widely?
Could you be louder, please? I did not get your question.
And which is the sector which uses digital technology widely among all the sectors?
Uh, that is very difficult to say because nowadays every domain they are trying to integrate GIS into their platforms as such. Like you cannot say that this particular sector is using more because of the technology, rapid technology development, and people are also trying to adapt to the technologies, right? So that is the reason there is like a lot of development. If you take like mining sector, there are like a lot of people who are flying drones, getting the images, processing it, doing volumetric calculations, and then generating outputs and calculating the stockpile volumes, and then helping in planning and everything. If you take mine, and if you take like environment, they will use for impact assessment, they will use for planning of the environment, planning of the industries, they'll use it for changing to find the change in the pattern of the land, and then to generate insights how the land has been changed over the past 10 years or 20 years in a given location. So if you take utilities, the same way, like how they plan their utilities, and like if at all, like earlier before fiber optical cables in the network placement, there used to be other technology, but when they replaced with the fiber technology or their existing customers or their potential customers, so they started integrating there. So it is not something like you can say only this particular department or this particular sector is only using it. Even if you take telecommunications, earlier you have 2G, 3G, 4G, and now people are adapting to 5G, and whoever or everybody in 2G, 3G, and 4G will definitely migrate to 5G. May not be now, but in a few months. So everybody is a potential customer. Even telecommunications are using it, and even the water distribution networks, even those people will adapt it. So it is not like some specific department is using it. It is up to us how we use the technology for our needs.
Yeah,
I mean, I have just told you few examples of the industry application, but there are like many more depending on
yeah.
what in what domain are you in.
Got it.
So any other questions? All right, thank you for joining us today, and we'll be sending you a feedback form. I request everyone to send their feedback so that it will help us to conduct better tech talks going forward. Thank you.
Thank you.